All right, hello and welcome. My name is Sean McKellar, and I'm going to be doing a quick presentation on an instrumentation activity for my Physics 3719 class. So let's go ahead and get started. The very first project that we were tasked with was building an analog to digital converter. And real quick, I'll explain how these work. Basically, an analog to digital converter sends a voltage to a comparator, and then it actually typically does some sort of sample and hold algorithm on this voltage. So maybe, if I send in 3.4 volts, it will stay 3.4 at this input on the comparator. And then there's another input to the comparator. The output, of course, is going to be whichever of these voltages is greater. Okay, so the very first time you hook up this ADC, the other input will be 0. So the output of our comparator will be whatever voltage we've sampled on our positive terminal. And that is getting sent into something called a successive approximation routine. What this does is it takes this input and it turns it into a binary number of, I believe, slightly greater value. And then the output of this, so it's a binary number, which is really just a voltage. The information it will carry is voltage. That gets sent to a digital to analog converter. So we send in a binary number, a digital input to this DAC, and it outputs a value which is approximately equal to that voltage that we tested here at VN. So it may not be 100% equal. And so we'll send it through the comparator again, and we'll keep doing this until it gets closer and closer and closer. So it's a pretty simple circuit, but it actually is in tons of modern electronics. And this is something that I think everybody should encounter once. I just realized that you may not be able to see my mouse, so let me turn on the laser pointer and zoom. Hopefully anybody watching was able to follow my description there. But here's the circuit that we built. So I have the DAC right here, and then a comparator circuit right here. You can see these inputs. One goes into the DAC, and then the other one goes into a voltage divider. And the output is essentially just sent over to an Arduino, which is running some sort of successive approximation routine. So pretty cool. You can actually read the values right off this little OLED screen. And so that's what I did. I took values at varying voltage measurements, and I graphed them. You can see my values enumerated right here. And I just graphed here the volts at the potentiometer versus the volts on the ADC. And they are very close. So I did an R squared fit to see how close they were. We have an R squared value of 0.93, which is pretty decent. So definitely there's a correlation here. So that was the first little task. The second task was to make a sine wave generator using Arduino code. And all this code was actually provided to us from somebody working for an Arduino company or some sort of similar small electronics company. But in this circuit, all I really have hooked up is the DAC. You can see that those the output of the DAC is being sent to the Arduino. So what we're doing is we're sending on the SCL and the SDA lines, we're sending information into the DAC, and we're telling it to generate a sine wave, and that's our output. And this output gets ported over to one of the analog terminals on the Arduino. Now, I would imagine theoretically it's possible to do this without the DAC. However, this is probably going to provide a more stable output. So the outputs I got were different sine waves. And I actually will have to come back and replace this image, which I'll put in my final report because it looks like these are the exact same images. But what I wanted to show was that you can actually change the frequency of this sine wave. So it's kind of interesting. For the next task, we were supposed to build passive filters. Now, I didn't actually have the correct components that I really wanted to in order to build a filter, but I've been learning a lot about filters this past semester, and so I think I came up with something a little better. At least it's what most electrical engineers do in the field. So I'll get into that on the next slide, but first let's just talk about passive filters. So the way a passive filter works is that typically you have a resistor and an inductor, or a capacitor and a resistor in series. And we know the impedance of an inductor is equal to j omega L, or the impedance of a capacitor is negative j over omega C. And so looking at these values, we can see that for very large frequencies, the impedance of a capacitor is going to be essentially zero or negligible. And so because of this, at large frequencies, this circuit doesn't actually pass any output. So this ends up being a high pass filter, what I've drawn right here. Sorry, I think I said that a little wrong, but the impedance goes to zero as omega goes to infinity, and so we pass signals at high frequencies. The opposite is true with inductors. However, in this configuration, you can see at a high frequency, we have a high impedance, and so no current will actually flow through the inductor at a high frequency. So this is actually also a high pass filter. Now, if we swapped these components here, then that would cause this to be a low pass filter using an inductor. And the same is, of course, true if we swap these components with the capacitor and the resistor. This would cause this to become, it would flip its behavior, is all I should say. So I actually went and designed some simple little introductions to passive filters using a program called ADS. It's a really cool simulating software, and you can do all sorts of design. It's used very widely in the field. So what I've done here is I threw together a little passive filter with a capacitor and a resistor in series. And I put basically two terminals down, and I'm measuring the S parameters. So the S parameters can do some really cool stuff. You could talk about them for hours and probably write a textbook, but in 10 seconds, the S11 parameter tells you the reflection coefficient. So if S11 equals 0.99 linear, well then that means I'm reflecting 99% of my energy. Anyways, so you can imagine then that there's also a transmission coefficient, which is exactly the opposite. Well, that's called S21. And you can see I've graphed both of these here for this circuit from 0 to 10 gigahertz. And this is in dB. So as you can see, there's this thing called the minus 3 dB frequency, and that occurs roughly right here. So at this frequency, we call this the cutoff frequency. Roughly, I believe like 30% of your energy is being reflected. So you're transmitting 70%. Now that's where we say this filter kicks in. So this is a high pass filter. Wait, did I get that right? One moment, let me. Sorry, I had to pause the recording for a moment, but so you can see at higher frequencies, we have like up to negative 10 dB. So this is passing, it's reflecting almost no energy at these larger frequencies. So it's passing that energy. That means this is a high pass filter. And that's just with a capacitor and resistor in series. So I went ahead and did the same exact thing, but I added a parameter sweep to change the value of the capacitor. So you can see how changing the value can affect the cutoff frequency. It's kind of cool. And so I believe this is as the capacitance grows, we end up with a higher pass filter. It passes larger frequencies. Or I should say it cuts off at smaller frequencies. But I went ahead and made a low pass filter by doing exactly the same thing. And here I've just included the little parameter sweeps. And So I wanted to include one more example of how you can use filters. There's tons of different ways, tons of different variations, but here's a pretty interesting one. So you can use filters to do something called matching. That's when you have some sort of load connected to a transmission line or some other system, and the load has a high impedance. Now, when you connect that to a transmission line, you're going to have a high amount of reflected energy if the impedance of this thing doesn't match that of the transmission line at a given frequency. And so one common thing to do, if this is the case, is to design something called a matching network. And essentially this is a filter. You can see I've put one down here, and here's another matching network. It's a filter that operates at a particular frequency, so that you can have your device in your system without reflecting energy back and possibly causing an explosion or who knows what. But so this is an example of a 2.45 gigahertz amplifier I designed, and it has a pretty high gain. But what we're going to do with it is hook it up to a 50 ohm transmission line. And so since this amplifier was actually designed from a 7 gigahertz amplifier, all I had to do was create these matching circuits so that now our amplifier can be hooked up to the system at 2.45 gigahertz, and it will have a high gain still at that frequency. So it's pretty fascinating, though, that you can use a filter to do this sort of task, in addition to many others. So it's quite a complex topic. I think I could talk about filters for hours, but that's all I have for now. Thank you so much for watching. Have an excellent day.